The next transcendental function we will look at are called hyperbolic functions, and I have them defined here already. So the hyperbolic sine, written as sinhx, is equal to, or defined to be, e to the x minus e to the negative x over 2. And you instead of saying hyperbolic sine all the time, you can say sinh. And then for cosine or hyperbolic cosine will be cosh, but that's how you would state it. So hyperbolic cosine, cosh, is the same format but just a plus in the middle. So there's e to the x plus e to the negative x. And then I have graphed these down here, and what I have basically graphed is 1/2, approximately 1/2 e to the x, and then negative 1/2 e to the x. It's basically flipping this down across the axis. And so if you look at the for sinh, if you look at the difference of these values, then this is how you get the graph of sinh. So you basically take each of these and you're subtracting them. And so as you get really large here, you're subtracting just a little bit down here. Like you're adding them, right? Adding a negative. So these are all the negative for this function. And then similarly over here for cosh, you have e to the x and then e to the negative x. So this one, by the way, is this graph and then flip down. That's what that is. But that's just one way to visualize it. So we know that e to the x and e to the negative x is any exponential function, b to the x, is always positive. It's positive for every x. And so you have these two. So the cosh is this graph is always positive. And for this one, you basically are adding these values to get the next value. So as you go closer to here, you're only adding a little bit, but it still grows like that. And so it has a number of properties, and it comes up in a bit of applications here and there. This is an application of cosh. So a is a constant here and here. And what this is called a catenary. And what it basically, what you can picture is you have two like poles or side of a building or something. And then you have a rope or a cable or something. And the way that hangs like this is what's called a catenary. And it isn't a cosine or sine or anything like that. It's actually a hyperbolic cosine. It's not parabolic either, right? So parabolic, I mean, it looks like maybe a parabola, but it isn't. It's this thing. So like power lines, like these are power lines right here, and they're hanging. The way they hang is this function. And so for long, like if you're just doing something real simple, you just estimate and then that's it, right? But if you're building billions of dollars worth of infrastructure, then you're going to want to model it using the actual function or something. There's probably more variables you could put in here. But the foundation of it is that. Okay, so let's go on. Let's talk about identities. We always like trig identities. So we're going to throw in a couple hyperbolic identities, or I'm going to prove one. So this is a hyperbolic identity. So there's a few of them. We'll just look at one right here. So one of them is cosh squared x minus sinh squared x is equal to 1. And we can prove that relatively easily by using the definition. What's nice about hyperbolics is everything we're doing goes back to this definition. So you just have exponential functions, and the derivatives are pretty easy, right? Integration is pretty easy when you just have that form. In fact, you could even break this up and do it separately when you do stuff. So if we just substitute these in and simplify, we should get 1. So let's go ahead and verify that. And this is always a good opportunity for me to show you how to do these. You do not say this is equal to 1 and do your stuff and then say 1 equals 1. That is not the way to do it. So that's assuming your conclusion is what that is. Logically speaking, you're assuming your conclusion. Do not do that. All right, so you start on one side, work to the other. So again, this is relatively simple, but I wanted to verify or show you again how to prove some of this stuff. So I'll even say that for you. Start on one side and work to the other. Now it would be kind of difficult possibly to start on the right-hand side, right? 1 equals what? I mean, you could say, 1 is equal to 2 minus 1 or is equal to, 4 over 4. But that makes it kind of difficult, right? So we're not going to start on that side. So we're going to start on the left-hand side, work to the right-hand side. So here's our definitions. I'll go ahead and bring these down. So we're going to use these. Move this one over. As we do this identity, prove this identity. So hyperbolic cosine is this whole thing squared. So you get, so start with the actual statement. So cosh squared x minus sinh squared x is equal to, and then put that whole thing in. It is e to the x plus e to the negative x all over 2. And then that whole thing is squared. Then it's minus e to the x minus e to the negative x all over 2. And then that whole thing squared. And so we can easily square that denominator here and get 4. So we'll do that. And then we'll just be squaring the numerator there. So this is equal to e to the x plus e to the negative x squared over 4 minus e to the x minus e to the negative x squared over 4. And now we expand everything out. So I'm not going to necessarily show that, but you get the product of these two is the first term. I'm sorry, the product of itself is the first term. Product of the second term is the last term. In the middle is the sum of this product. It's twice the sum of this product. So what you get then, and then remember that a couple of things. E to the x, e to the negative x is equal to 1. E to the x quantity squared is equal to e to the 2x, and some other exponential properties we'll be using. So it's e to the 2x plus 2 e to the x, e to the negative x. Right, it's twice this product. Outside is plus e to the negative 2x. Then it's minus quantity, e to the 2x minus 2e to the x, e to the negative x, plus e to the negative 2x. And then we can go, I mean, we don't have to show that whole expansion. That's all over 4. Right, because you're just subtracting those. So what you have then is you have your this term and this term are going to cancel. Then you have this term and this term will cancel out. And then we're going to use this concept here that e to the x, e to the negative x is 1. So these are both equal to 1. And so you get, this is equal to 2 minus negative 2 over 4, which equals 1. And we have just proved it. So it's a good exercise to go through. If you didn't follow all of that, I would do it on your own. This is one I often ask on an exam just to practice it. By then, you're usually pretty good at doing it, but it shows all these steps. Probably not on this one in this class because it's like right there. You just copy it. So it's a little different. But all right, let's look at some more stuff. Let's see. Yeah, we'll do one more thing. Let's do derivatives of hyperbolic functions, and then we'll stop for this video. Okay, so derivatives of hyperbolic. Functions. Again, these are actually pretty easy and fun to do because it's straight up simple. So d dx, I mean, that's in a relative sense, of course. Sinh x ends up being cosh x, which is really just like sine and cosine. But then d dx of cosh x is just sinh x. So no negative, in other words, for hyperbolics. So let's do a little proof of that. And you just use the definition to prove again. So you say d dx of sinh. Oh, and you'll, just a thought, you'll see all these on your calculators or your phone emulators or whatever. You'll see sinh and cosh on there. Not all of them, but if you look, you'll find a menu that has those. So then let's just say that it's d dx of the definition. So the definition is, for sinh, it's e to the x minus e to the negative x over 2. And so we are taking the derivative of each of those terms. I'll go ahead and write it out. So it's d dx of e to the x over 2 minus d dx of e to the negative x over 2, which equals, and so now we're taking these derivatives independently, and so this is itself, right? You just factor out the half, and then each derivative of e to the x is e to the x. So this is just 1/2 e to the x. And this one, we need to use chain rule, so it's itself times the derivative of the top, which is -1. So you get a plus, 2 negatives there become a plus e to the negative x over 2. I don't like to mix my forms there. So this is 1/2 e to the negative x. And if you rewrite that, or that is basically e to the x plus e to the negative x over 2, which is equal to cosh. And then you just, the similar thing for hyperbolic cosine, you just do that. I won't show you every step here, but if you do d dx of cosh x, then you just put in the definition d dx of e to the x plus e to the negative x over 2. And then you can see here that it'll be the same stuff, but you're going to bring that negative down. So that middle term here becomes negative. And so you get sinh x. And then, so when you integrate these, they just go back and forth, right? So you integrate d dx, you get cosh, which is sinh, and then you integrate this and you get, so they just go back and forth for derivatives, which makes them really nice to work with, generally speaking. So you get, so just a couple integral formulas from above. Integral of cosh x dx is equal to sinh x plus an arbitrary constant, of course. And similarly, integral of sinh x dx is equal to cosh x plus c. Okay, and that's just using what we know as the derivative and going backwards. So, okay, moving on. A couple examples. Let's do this one. So find f prime of x if f of x is equal to cosh of x squared plus 1. Okay, so that's pretty straightforward stuff, right? So f prime of x is equal to, so what do you need to do here? The derivative of cosh is sinh, so it's sinh of all this, and then times what's inside using the chain rule. So this becomes just 2x sinh of x squared plus 1. Okay, so that's just applying chain rule basically. Next one, evaluate the indefinite integral of x squared sinh x cubed dx. And you can see here now you got to think u substitution. So we do u sub, and then take the derivative of what you're substituting for. Do you get something to equate to? Like, do you get something in here? And yes, you do, right? I mean, if you do take this to be your u, then your du has x squared in it, which is exactly what we're looking for. So let's let u equal x cubed. This is a good spot to work it on your own. So try it. Okay, so then du is equal to 3x squared dx. So du over 3 is equal to x squared dx. And so you have, so your x squared dx is right here. And that becomes your du over 3. And then you substitute for your u, of course. That's your u. So this is equal to, I just put it equal to, integral of, and so the 1/3 comes out. And then that's just sinh u du, making all those substitutions. And then this becomes, you don't have to worry about signs here. That's just 1/3 cosh u plus c. And let's move this over. And so you just now substitute back for your u. So it's equal to 1/3 cosh, what was u again? Oh yeah, it's x cubed plus c. Okay, so that's just how you would apply that. I just messed it up. How you would apply that. Integrals and derivatives. So once you know the basic foundation of it, then the rest is similar to what we've been doing. Just adds on to it. Okay, we're going to work through inverse hyperbolic functions. And quite frankly, we're not going to use them a lot through the rest of the book. However, the derivation is worth looking at, and it uses a lot of techniques from the past that you may have wondered, why the heck are we doing them? So I want to go through it. It's a good derivation to find the inverse hyperbolics and how they're defined. And then, I mean, they do come up. So let's take a look at that. And then that's about it. There should be one more video here.